Okay, so now we're actually ready to conduct some full hypothesis tests from top to bottom using Excel for help. We're going to start with a z-test, and then we're going to do a t-test after that. We use a z-test the same as when we use or create a z-confidence interval, which is when the standard deviation of the population, sigma, is known. Now, regardless of which one of these tests that you end up performing, the basic kind of 5 steps are the same. First, you're going to write your hypotheses. That's the null and the alternative. You're going to write those. Decide on your significance level alpha. So if you're really performing one of these, you decide. For us, we're going to use whatever they tell us to use. Compute either the z or the t test statistic and the p-value. Compare that p-value to the chosen alpha in order to reject or fail to reject the null. And then write your final conclusion in context. And that last step is so important because that's what ultimately goes out to the public and gets published anywhere, is the contextual conclusion that you reached. Okay, so do not let that part fall by the wayside. That's actually the most important part of what we do. Now here is how we calculate the z and the t statistic. Notice that it's basically like the z-score formula, where we take the data value in question. For us, that's the sample mean, x bar, subtract the hypothesis mean, mu sub 0, and then we divide that by, and here's where things change a little bit. For the z, we divide it by the quantity sigma over the square root of n, because we know that population standard deviation. Whereas for the t statistic, we divide it by the quantity s, or the sample standard deviation, divided by the square root of n. So we have to do that part for ourselves. Okay. For our example, we are going to revisit the computer hardware installation problem that we did in our confidence interval section. So this should look familiar to you. In that section, we created a 95% confidence interval for the population mean, and we happened to get the interval 40.67, 44.64 for that. So we were 99% confident that the true population mean was somewhere in that interval. So you want to open that install and delays data again, and install is the first page. As a reminder, the mean install time, this is new for this particular problem, sorry. The mean install time for this hardware has been thought to be 40 minutes for some time. So that's like the accepted value. That's where our null is going to come from. This is what we think it is. But this researcher believes that the mean install time is actually longer than 40 minutes. So that's what he is trying to show. That's the alternate hypothesis, or when we write it, that's where it's going to come from. We know from the prior information that we were given in our prior section that the standard deviation of install time is definitely 7 minutes. So that is that sigma value. That's why we are able to use a z-test here, because we know sigma. We also have the same 50 computer data set. So that is our n value. N is 50. And we want to perform a hypothesis test with this information using an alpha value of 0.05. Okay, our first task is to write our null and our alternate hypotheses and decide whether it's a 1 or a 2-tailed test. So I'm going to write h sub naught and h sub a. My null hypothesis is that we think, or we've all been told, that this mean install time is 40 minutes. So that mu equals 40. But we are researching the idea that maybe it's actually, notice it says longer than 40. So we have direction here. So we're hypothesizing that mu is greater than 40, a longer time than 40. This is a 1-tailed test, because we have direction there in the right-hand direction. The first thing we need to do is find the sample mean X bar. So we're going to do that in Excel by doing the equals average command, because we need to find the average of our data set, the average of this sample. So in the X bar area, I'm going to write equals average. I'm going to highlight all of the data here, close it up, and we get 42.7, and that should look familiar to you, again, if you followed along in the confidence interval section. So again, do you know how to calculate an average by hand? I'm sure you do, but this is a large data set, and remember that data sets could get much, much larger than even 50 entries. You do not want to do those things by hand. Use Excel. That's why we're learning Excel. Okay, identify mu sub 0, sigma, and n. So we get all these bits of information from the question. So mu sub 0 is the hypothesized mean, so that's that 40. We think that it's 40, and we're hypothesizing about that. Sigma is the population standard deviation, which in this case was 7 minutes, and n is 50, a size 50 sample. So with that information, we can now compute the z-test statistic, because we have all of the values we need to sub in there. So z is calculated by doing x bar, so 42.7 minus mu sub 0 is 40, over the quantity of sigma over square root of n, so 7 over square root of 50. So the top is easy to calculate, that's just 2.7 over. Now what you want to be very careful about when you're doing this in your calculator is that you insert parentheses around here. If you divide without putting in parentheses, you will only divide by the 7, and then you will actually end up multiplying by the square root of 50, which is not what you want to do. You want to divide by all of that. So I might type this in as 2.7 divided by parentheses, 7 divided by, and then you can get your square root by doing second and the x squared button, so square root of 50, and then we can close that up. Okay, so make sure that you're really dividing by everything that you intend to divide by. It looks like that value is about, I'm going to keep 3 decimal places here. I'm going to call that 2.727. Watch for any rounding directions in your questions. Now we are going to find the p-value. How you find the p-value here is determined by, we're going to look at I'm looking at our Word document for how we perform these hypotheses tests. So you're always going to use the equals norm.s.distribution, and it takes 2 values. It takes the z value that you just calculated and a true. But notice that what you do after that depends on whether it's a right or left tail test or a two-tailed test. So if it's a left tail test, the output that you get from doing this command is your p-value, right? Because it always calculates the value that Excel does to the left. If it's a right tail test, you're going to have to take that area and subtract it from 1 in order to get the right tail. And if it's a two-tailed test, notice what you do. If z is negative, you take the output times 2 for the p-value, and if z is positive, you take 1 minus this output times 2. So I'm not going to go through every single one of those scenarios. That's your directions right there for what to do. Refer to that whenever you're doing your assignments. For us, we have a right-tailed test, right? We were doing greater than. So we are looking for, we just got our z-test statistic being 2.727, and we're looking for this p-value area over here on the right. Excel will automatically calculate the left tail, so we have to do a subtraction step. Okay, so when we calculate, I'm just going to do it over here. We're going to do equals norm.s.dist. The z value we got was 2.727. We always say true here because we want the cumulative area, not just one value, but the whole area under that curve. So what we got out of Excel was we got a 0.996804. But remember, that's this area always from Excel. That's not what we wanted. So we want to do 1 minus that. So I'm going to just type in 1 minus and then grab that cell right there. Sorry, 1 minus. So what I'm going to say here is that's the cell E3. Oops. Equals 1 minus E3. Okay, so my actual p-value then is 0.003196. So as a reminder for what we did for your future, we wanted to do 1 minus this value, the norm.s.dist of 2.727 true. So we actually got 1 minus, and as a reminder, that value came out as 0.996804. So we got 0.003196. Okay, that's what we need Excel for. Now, the rest of it we can do on our own. We want to compare this p-value to alpha and draw our final conclusion. So you have to be able to compare decimals. So the p-value we got, this is p, 0.003196, how does that compare to 0.05? It is less than. So since p is less than alpha, we reject the null. Don't stop there. Tell us the conclusion in context. So we've rejected the idea that it's 40, and instead we have enough information to conclude the mean is greater than 40. So we can conclude that the mean install time is greater than or longer than 40 minutes based on this.